Hi, I'm Nathan Stovall, and I've had the privilege of working in the lab of Professor Shannon Betcher. And what we study in the Betcher lab is clean energy technologies. And specifically, I've studied water electrolysis or water splitting. We split water, H2O, into its constituent components of hydrogen gas and oxygen gas. This happens generally in industry as in a proton exchange membrane water electrolyzer. This is state-of-the-art technology where you have an anode where you do the oxygen evolution reaction, or OER, where you split water into protons and oxygen gas. These protons then travel across this Nafion membrane to the cathode, where they recombine with electrons to form hydrogen gas. And this hydrogen gas is extremely useful as it can be used as a way to store clean energy over a long period of time. You just run this reaction backwards to get the energy back. But actually, I studied the oxygen evolution reaction, interestingly enough. So why do I want oxygen if we really want hydrogen? Well, actually, you can't get one without the other. You have to do both. And it turns out the oxygen evolution reaction is rate determining. It limits the rate at which you can split water. And to aid in this, we want to develop a catalyst. But unfortunately, due to the acidic conditions of this Nafion membrane, really only iridium has shown to be a active catalyst that's also stable in the acidic and oxidizing conditions of OER. But unfortunately, as you can see on this bar chart here, that if we wanted to get hydrogen on the terawatt scale, we need 400 tons of iridium, which is 40 times the amount of iridium we even mine yearly. So that's where my research comes directly into play. I'm trying to work to understand how we can limit the amount of iridium on the surface of our catalyst to make water splitting cheaper and easier to maybe implement on wide scale, gigawatt scale, economy scale hydrogen production. And to do this, I developed a synthetic route to an iridium monolayer. You have a metal oxide substrate, and then you spin out another metal oxide, in this case, antimony doped tin oxide, on top to increase the catalyst conductivity. And then you can actually take this iridium COD dimer here and soak it in organic solvent in air-free conditions and mount these and mount iridium onto the surface of your metal oxide and then anneal to remove your organic ligands, giving you this ultra thin iridium catalyst. And we also find that these hydroxyl groups limit the reaction on iridium. You see in this UV-vis data, the concentration of our dimer here eventually will level out no matter what solvent conditions we use, meaning that when this levels out, the reaction is stopped. And that gives us precise control over the atomic architecture of our catalyst. And interestingly enough, too, if you anneal and get hydroxyl groups again on the surface of your material, you can add additional iridium layers if you choose to do that. But now we've made something, but does this something work? Does the catalyst work? Is it effective? And a test that we ran, an electrochemical measurement called Cyclic Voltammetry, you sweep through a potential range and you measure a current response. And we actually see here that our catalysts, or these two choices on the left, we see they have much more current and than their iridium oxide nanoparticle counterpart at much lower voltages, meaning we're losing less energy during the water electrolysis process and therefore making the process cheaper and faster. So we see that the low loading iridium catalyst actually outperforms what was previously thought of as the state-of-the-art iridium oxide nanoparticle catalyst. And then we got greedy. We said, can we make it more active? Can we further tune the electronic structure of our catalyst and increase the activity? And we could, we could add TiO2 to our catalyst, and we see that it increases the activity even more. And interesting, that doesn't make it any less stable, which kind of breaks this activity stability inverse relationship that people will often see in the literature. But it's still not that stable, is what we learned. Is looking at this trace here on top, this is just showing the potential we're applying within our electrochemical cell related to the axis here on the right. And down here, we have this noisy ting signal, and then your iridium signal related to this axis on the right. And essentially what we see is as we increase the potential up into what I'll call OER relevant regions, we see spikes in this bottom trace, in these bottom traces here. And what that means is that we're actually losing catalyst on the surface of our electrode. It's falling off or it's dissolving. And that's definitely problematic, as if we want to be able to run these devices and implement them widely across the nation, across the world, we can't have catalysts that are unstable on the surface of our electrode because the device will start to lose its performance very quickly. But what can we conclude from what we learned so far? We have a lot of positive results, and we found you can synthesize a low-loading iridium catalyst on metal oxide support and be atomically precise over the nano architecture of the catalyst, adding different metals to tune electronic structures and increase activity significantly. And further, we observed significantly increased intrinsic activity compared to the state-of-the-art iridium oxide nanoparticles. However, the stability remains a problem. And lastly, I want to say thank you to a few people, Dr. Shannon Betcher for allowing me to work in his lab and providing me enormous opportunities. My PhD candidate mentor, Raina Corvina, for being an incredible mentor and teaching me pretty much everything I've learned in the lab, as well as the Phil and Penny Knight campus for accelerating scientific impact and the UO Office of the Vice President for Research and Innovation for providing me funding through the Knight Campus Scholars Program to perform a lot of this research. Thank you.